Hello and welcome to the second lecture of the second part of the course Introduction to General Relativity. Let me remind you that the second part is called Mathematical Preliminaries, and this part is designed to equip you with the tools of differential geometry and Riemannian geometry which are necessary to work in warped spacetime, that is spacetime with gravitational fields turned on. I'd also like to point out, although I'm calling this lecture 2, lecture 1 was 1 hour duration, and it's split into 2 parts on the NPTEL website. So technically speaking, this is lecture 3. In fact, this lecture is also going to be close to an hour duration. So it is split into 2 lectures, which is lecture 3 and 4 of week 7, or lectures 40 and 41 overall. All right, so the main reference for this lecture, which is intended to familiarize you with some elementary ideas from differential geometry, is chapter 5 of Nakahara's text. Page numbers are indicated here. Carroll's lecture notes, chapter 2, these pages, and Hawking and Ellis, chapter 1, these pages, also cover similar material, so they can be treated as an alternative reference for this lecture. As usual, the lecture notes will be posted on the NPTEL/SWAM website. And for those who want some more details or more depth, can consult Warner's excellent text, but I should caution you that Warner's text is actually a graduate level mathematics text, so that might appear a bit challenging or formidable to some physics students. So I'll assume certain background for this lecture. I'll assume familiarity with what a topological space is and what open sets of a topological space are. I'll assume people are familiar with the standard topology on Rn, which is the n-dimensional Euclidean space. Also assume people are familiar with what is the Hausdorff space, or what is the Hausdorff property of the space. In the literature, people also refer to it as the T2 space. So T is for the Russian mathematician Tikhonov, so this is also called the Tikhonov 2 space. And I'll also assume familiarity with the concept of the cover. So you can find all these topics covered in the first lecture. Please refer to the previous lecture if you want to recall what these are. So the agenda for today's lecture is the following. Our aim is to become familiar with the concept of an n-dimensional differentiable or smooth manifold. Now, mathematicians would draw a distinction between a differentiable manifold and a smooth manifold, but from the point of view of GR, we will not distinguish the two. Whenever we say differentiable manifold, I will mean smooth manifold. So I'll use these two terms interchangeably, although pedantically speaking, they are different. Maybe I'll point out to the difference in the lecture. We'll learn about charts and atlases of a differentiable manifold. We'll learn about coordinate functions, and we'll learn about transition functions. Now, this transition function is the same as passive coordinate transformations in the language of physics. So of course, these are important because these represent general coordinate transformations, which is the symmetry of general relativity, as you must have known already. We'll learn about compatible atlases, what is a maximal atlas, and the associated differentiable structure. And finally, we'll learn about smooth maps between manifolds. We'll learn about a special category of smooth maps, which are invertible, and the inverse is also smooth. These are called Diffeomorphisms. And we'll learn about the group of Diffeomorphisms of a manifold M back to itself, which is given by the symbol diff of M. And these represent the active transformations, okay? So these are also important as an active way of thinking about general coordinate transformations. All right, without further ado, let me begin the lecture. The first thing we want to learn about is the concept of a differentiable manifold. So, in general, differential geometry actually generalizes the Euclidean geometry of curves, smooth curves and surfaces embedded inside R3 or R2. Most of you have taken a class in solid geometry, or even in college. In your first year, you must have had some coordinate geometry. There you might have learned about smooth curves and surfaces embedded inside R3 or R2, which is a three-dimensional Euclidean space or two-dimensional plane, Euclidean plane. And the concept of manifold actually generalizes this idea of smooth curves and surfaces embedded inside R2 or R3 in a more abstract way, in a more general way. All right? So this is the origin of the subject. Let me start with the definition of an n-dimensional differentiable or smooth manifold, denoted by m raised to the n. I will read it as mn. So Mn is a Hausdorff topological space. This is the first condition. Second condition is that Mn is covered by a countable collection of open sets, U sub I. So this U sub I, with I labeled with integers, positive integers 1 to n, for example here. This big N has nothing to do with this little n, which I will explain later what this is, which is called the dimension of the manifold. So the number of open sets which are covering M has nothing to do with the dimension. So that's why I distinguish them. One is little m, the other is big N. Alright, so we have a countable collection of open sets which are given by U sub I. This curly bracket means it's a collection. And then union of these UIs give me the manifold Mn. Okay, so the union is M. Sometimes I will omit the dimension and I will just call the manifold to be M. Okay, so the third condition is that each of these open sets which are covering the manifold, each of these open sets, they're homomorphic to an open set in Rn. So let me, perhaps it's better to draw a picture. So if I have some manifold, it might be covered by 3 or 4 such open sets. So the union of the 1, 2, 3, and 4. So these union of these gives you the manifold. Each of these open sets, let's say this is U1. This can be mapped to some open set in Rn. For example, an example of an open set in Rn is an open ball, for example. So this U1 area or U1 open set can be mapped entirely to an open set in Rn. So this is Rn with Cartesian axis. So this is what people mean when they say, colloquially say, that a manifold is something that locally around the neighborhood of a point, the neighborhood of the point looks locally like Rn. Okay, that means each open set of a manifold which covers the manifold is homomorphic to Rn. So homomorphic, so I should draw a double-headed arrow because it's homomorphism is a invertible map. So these homomorphisms from these open sets U sub I to some open set of R, then for example O sub I, these homomorphisms are denoted by this phi sub I. Okay, phi sub I is the homomorphism. Okay, and finally, when P is the point which lies in the overlap of two open sets Ui. So you have a manifold, and let's say you have 2 open sets which cover a certain part of the manifold. Let's say Ui and Uj, and let's say you have a point P which lies in the overlap. Now, because P lies in the overlap, it can have 2 set of coordinates. I'll explain a bit later. But the idea is that these functions, phi I O of phi j inverse, these are called Preliminaries-1 functions. Basically, what they do is write the coordinates of the point P on the second chart or second open set are smooth functions of the coordinates on the first open set. This I will explain a bit later in the next page, in the next slide. So these are smooth functions, and smooth function in the sense of multivariable calculus, because as I will show in the next slide, that these are functions from Rn to Rn. Okay, so this is usual multivariable calculus which you learn in your first year of college, and these are smooth functions of each other. So a smooth function, I will explain in a bit, or C infinity, what this means in the next slide. All right, so this next slide is the diagram which I drew before. So we have a manifold which is covered by 4 open sets, U1, U2, U3, and U4. U1 is everything to the left of this red boundary. U2 is everything to the top of this blue boundary. U3 is everything to the right of the green boundary, and U4 is everything to the bottom of the yellow boundary. Okay, so the union of all four gives you M. And I've indicated here, for example, U1. For U1, there is a homeomorphism phi1, phi sub 1, which maps it to some open set in Rn. In this case, the open set happens to be an open ball, but not necessarily, as we know that the open sets of Rn are given by open balls as well as arbitrary unions of open balls and finite intersections of open balls. Okay. Similarly, U2, the second open set, also has its own homeomorphism, which maps it to another open set in Rn, which is given by O2. And this point P, which I have not indicated, lies in the union of U1 and U2. All right. Right, I hope things are clear. Let me go to the next slide, where I introduce some terminology. So this number n is called the dimension of the manifold. Remember, as I said, a manifold, the open set of a manifold is always mapped to some open set in Rn. So open set in Rn. So this n of Rn is called the dimension of the manifold. This is what we call Mn. Okay, dimension. And then this pair, each open set with its associated homeomorphism, which takes it to an open set in Rn. This pair is called a coordinate chart in the math lingo, and in the physics lingo, it's called a coordinate system. You will see why it's called a coordinate system in a second. UI itself is called the coordinate patch. Okay, UI phi I, this pair is called a coordinate chart, but the first entry in the pair used by the open set is called the coordinate patch. You'll be hearing me saying this, using this terminology, coordinate patch, a lot of the time, so please commit it into memory. And this homeomorphism phi I, which maps UI to an open set in Rn, is called phi I. This is called the coordinate function, or simply the coordinate. What does this mean? Well, if I take a point P, which lies inside, so P is a point which lies on the coordinate patch. It's a point on the manifold. In particular, it lies inside this coordinate patch UI. Now, if I apply this homeomorphism phi I to P, I end up on the Rn, a point on Rn. And a point in Rn is given by this n tuple of real numbers. So the x1, x2, xn. This is called the coordinate of the point P. Okay. So you see, this is why we call it a coordinate system, because every point, courtesy of this homeomorphism phi I, gets a coordinate, n tuple of real numbers. Now, instead of using this explicit notation, list notation, I will always denote the coordinate by little x. And sometimes I will always also use the set builder notation, in which the component of x I will include by this abstract index notation, x mu, and curly bracket means it's a list, okay, where mu takes values from 1 to n. All right. So coordinate patch, coordinate function, or coordinate, simple coordinate. These terms you should learn. And if P lies in the overlap of two charts, then there are two coordinates for the point P, right? As I mentioned last time. So let's say this is the lower one is UI, the left one is UJ, and P happens to lie in the overlap region. Now, because P lies in UI, the homeomorphism phi I will assign to P a coordinate x, and because P also happens to lie in UJ, the homeomorphism phi j will assign another coordinate to P, which I'm calling y. Okay. Now, of course, this is a homomorphism, so these can be inverted. So P can be written as phi I inverse of x. All right. Now, these transition maps are so phi j of P P I can write as phi inverse of x. So if I substitute in P phi inverse of x, I get phi j of phi inverse of x. So y equals to phi j of phi inverse of x. So y's are given as some functions of x. We can do the opposite thing, that invert this equation to get P as phi j inverse of y, and then plug in the argument here, phi j inverse of y. So I'll get phi I of phi j inverse of y is x. So that gives you the coordinates x as a function of the coordinates y. Okay. So in simple language, I can write, the first equation I can write y as a function of x, and the second equation is x as a function of y. Now, the property of smoothness of a manifold means that these functions which convert one set of coordinates to the other, they are smooth functions in the sense that all ordered derivatives of the components of y with respect to the components of x, and all ordered derivatives of the components of x with respect to the components of y are finite. Okay, so these values are finite. Actually, we want a much more stronger requirement, which is that they are not only finite, but y is an real analytic function of x, and x is a real analytic function of y. That means the Taylor series expansion in powers of y as a function of x, meaning y can be extended in a convergent power series expansion in x, and vice versa. If x is an analytic function of y, that means x can be expanded in a convergent power series expansion in y or components of y. All right. So this is how we define a smooth function. All n order derivatives exist. All right. Let me give some examples. The first example is, of course, Rn. This is sometimes called the trivial manifold, and I'll explain in a minute why. Now, Rn is, of course, homomorphic to itself, right? Not only that, one can choose an open set O1 of Rn which is infinitely large. That is Rn itself. Okay, Rn itself is an open set because if you remember the axioms of topology, the axioms are that the full set and the null set members are both open sets. So I can include O1 to be the Rn entirely, and then the homomorphism would be just the identity map. Okay, so then Rn can be covered by a single coordinate pad or single coordinate chart. So any manifold that can be covered by a single coordinate chart is called a trivial manifold. Okay, in some sense, it is there's no distinction between that manifold and Rn. All right, a trivial manifold. In terms of the differential geometry, we won't distinguish between the names. If it can be covered by a single chart, it's as good as Rn. Okay, so let me give you a bit more non-trivial example, which is the unit circle, S1. S1 is the unit circle. This is the example of a non-trivial one-dimensional manifold. Okay, you might be thinking that, okay, but I can cover the unit circle by a single coordinate, that is theta, angular coordinate theta. That is some reference line, and with this some point P on the circle can be given by this coordinate theta. But theta can take values between 0 and twice of pi. However, this is not going to be an open set of R1, because this interval 0 to 2 pi with 0 included, but twice pi is excluded, half closed, half open. This is not an open set. This is not an open interval, hence it is not an open set in Rn. Okay. You might say, well, what prevents me from taking this open interval 0 to twice of pi? 0 to twice of pi. So if we take the open interval, then this point will be excluded because neither 0 nor twice pi is included. So you might take the closed interval. But then if you take the closed interval, it's not going to be an open set of Rn. So no single open set of Rn can cover the circle, actually. What you can do is you can take, you can cover the circle by two charts. For example, you can take a chart in which theta takes value minus pi plus delta to delta. So as you can see, this will cover. So if this is So minus pi at this point, so minus pi plus delta means it starts from a little bit above that and it covers plus delta. Delta is very small. Delta you can take to be infinitesimal, very small. And then this covers the lower half, including the points on the equator. And I can take theta bar to cover the upper side, which would be something like this. Minus delta to pi plus delta. Again, delta is infinitesimally small, so that will cover minus delta, meaning it will start from somewhere a little below, somewhere here, and then it will go cover the upper half entirely, and pi plus delta means slightly under, below this x-axis. Okay, so as you can see, these two, the union of these two definitely covers S1, and in the overlap region, which happens to be these 2 points, this point and this point, in the limit when delta goes to 0, only the 2 equatorial points are the overlap, the union of these 2 coordinate charts. So union would be theta equal to 0, this point, and theta equals pi. So, but in the overlap region, we know the 2 thetas are equal, both of them are 0, theta and theta bar are 0. So the transition functions are given by theta equals theta bar, which is of course a smooth function. Hence, you can think of this construction as giving coordinate charts or coordinate systems for S1. You need at least 2. Okay. So, but this is not very commonly used. Most books give you an alternative coordinate representation for the circle. So let me just go through that. That is called the cartographer's projection, or some people call it the stereographic coordinates. There you use 2 charts. One is called the North Pole based chart and the other is called the South Pole based chart. Let me just quickly explain what that is. So again, here I've drawn the circle twice, and this green line is of course R1. So the idea is that these charts should map the circle to some open set in R1. And the way you construct these for the north-based coordinate system or North Pole-based coordinate chart is in this way. Take a point P, arbitrary point P on the circle, and then join P to the North Pole by a chord, and extend that chord all the way to the real line and see where it lands on the real line. For example, if NP, this chord, if you extend it, it lands on this point P prime on the real line, okay? And then this length or line of the length segment or the intercept OP prime gives you the coordinate of the point P, x of P. Okay? Same thing for the South Pole based coordinate system. This point P, you join it to the South Pole via this chord SP, and wherever this the chord SP intersects the x-axis, for example, this point P double prime, that gives you the coordinate of the point P in the South Pole based coordinate system, which is the length of the line segment OP double prime, length of the intercept OP double prime, and this we will denote as Y of P. Alright, so these are 2 different coordinate charts. Now, why do we need 2 different coordinate charts? Because for the North Pole based coordinate system, the North Pole itself is not covered. We can see this heuristically in this way. Construct the coordinates of various points on the circle. For example, the South Pole, if I draw a chord all the way, it passes through the origin. Hence, the South Pole is given by x equal to 0. Coordinate of the South Pole is x equal to 0. Points a little bit to the right of the South Pole, but on the lower half of the circle, it will have some intercept which is positive but less than 1. Okay. Similarly, if I draw points to the left of the negative coordinate, but the magnitude of the coordinate will be less than 1. Now, if I come to the points which are on the upper half of the circle, as I've drawn for the point P, If I further go to points closer to the North Pole, the chord will keep on increasing in length. And at the North Pole, the coordinate will become plus infinity, or if you're approaching the North Pole, from the left side, the North Pole chord will go to minus infinity. So the North Pole doesn't have a definite coordinate. It has an indeterminate coordinate, because once you're getting minus infinity, from the right, you're getting plus infinity. So this North Pole based coordinate system excludes the North Pole, okay? It excludes the North Pole. Similarly, the South Pole based coordinate system excludes the South Pole. And mathematically, you can also arrive at the same conclusion using elementary trigonometry. So these are the coordinates x and y in terms of theta, the angle made with the x-axis. And you can see that the North Pole based coordinate system breaks down when theta equals pi by 2 and the denominator goes to 0, and this expression becomes ill-defined. Similarly, for the South Pole based coordinate system, the South Pole, which is located at theta equals minus pi by 2, the denominator also vanishes, and this expression becomes ill-defined. But in the South Pole based coordinate system, you can give coordinates to the North Pole. In the North Pole based coordinate system, you can give coordinates to the South Pole. So that together they cover the whole circle. Okay. And finally, the transition function is smooth. In the overlap region of these two North Pole and South Pole based cartographers for stereographic coordinates, this overlap region is the circle minus the two poles. Okay, S1 minus N minus S. Remember, N is given by x equal to N is given by y equal to 0, and S is given by x equal to 0. So x equal to 0 and y equal to 0, these points are included. Now, from this elementary trigonometric relations, you can easily infer that the product of this gives you 1. So xy equals 1, which means that y can be written as 1 over x, or x can be written as 1 over y. Either way, since x equal to 0 and y equal to 0 are excluded, these are smooth functions. You can take infinite order derivatives and they will all exist. Okay? They will all exist. Apart from these two examples, Rn and S1, there are other manifolds which are very common. For example, the n-dimensional Euclidean space. Again, it's a trivial manifold, as I mentioned. You can have the n-dimensional unit sphere, n-sphere. And then you can have Tn, which is the n torus, which is a Cartesian product of n copies of the circle, unit circle. So you can liken this to Rn, where Rn can be written as the Cartesian product of n R1s, right? Rn can be thought of ... Cartesian product of n copies of R1. Similarly, the n torus can be thought of as n copies of the S1. Also, another manifold which features quite prominently in physics is the real projective plane, RPN. I'm not going to explain this here, but please look up Nakahara's text for more details, which explains what RPN is. So these are something you should be familiar with, some simple manifolds. Now, let me come to the notion of an atlas. The collection of all coordinate charts, A. So as you can see, curly bracket means it's a collection. And we have these pairs, which are coordinate charts, u sub I and phi sub I. These pairs are gathered together into a single set. That set is called the atlas, okay? Which covers the differentiable manifold. We gather them in a single set, and that is called an atlas. This is very, you can see the parallel with what you have in your elementary geography class in school. You have books which are called atlases, having a lot of maps, and you have charts or maps on each page, and the collection is called an atlas. All right. Now, nobody said that the atlas is unique. In fact, you can have multiple atlases for the same manifold. So here I'm considering two such atlases, A and A bar, or curly A and curly A bar. And the pairs in the barred atlas are indicated with bars, for example, uj bar and phi j bar. And the number of such coordinate charts in the second atlas is also n bar, big N bar. So in order to draw a distinction from the first atlas, which has n charts, and the second atlas, you have n bar charts. N bar is not necessarily equal to n. Okay. Now, two such different atlases, if their union is for two such different atlases, if the union A bar, which is the set of coordinate charts from both atlases, is also an atlas, then the two atlases are said to be compatible. Now, what do I mean by the collection, the union being an atlas? That means the inter-chart transition functions are actually C infinity. Okay, so as you can see, phi I of phi j bar inverse and phi j bar of phi I inverse. These are inter-atlas transition functions. That is, I take a random chart from the first atlas and I take a random chart from the second atlas. So something like this. And in the overlap region, the coordinates of one, for points in the overlap, the coordinates of one chart is a smooth function of the coordinate of the other chart and vice versa. Okay, if that happens, then the union becomes a larger atlas, and we say that the two atlases are compatible with each other or equivalent in some sense. All right. Now we can keep on doing this process. We can start with one atlas and then add one more atlas which is compatible, add a third atlas which is compatible to the two of them, add a fourth atlas which is compatible with all three of them, and we can keep on adding such atlases which are compatible with all the existing atlases in atlases. Then at some point we will stop and we get the largest possible atlas, which is said to be the maximal atlas. So let me define it. An atlas is said to be maximal if it contains all possible compatible atlases. Okay. So the maximal atlas contains all possible compatible atlases. And from physics point of view, this is what we will work with. Now, when we have a maximal atlas, it is said to endow the manifold M with a differential structure. Okay. So specification of a maximal atlas is equal to or equivalent to specifying a differential structure to M. Now let me go why we work with the maximal atlas. Next point. From now on, we will always work with the maximal atlas for a given manifold. As you can guess, each manifold is supposed to represent a space-time in GR, and we will work with the maximal atlas because maximal atlas contains all possible coordinate charts which are compatible, which are smoothly, which are compatible, and these will represent all possible general coordinate transformations (GCT) here. I hope this is an abbreviation which is now going to be familiar to all of you from the previous lectures. GCT means general coordinate transformation, that is the same point in different reference frames or different coordinate frames. Okay, so maximal atlas means we allow maximum freedom in doing general coordinate transformation. So from now on, we will denote the manifold by this pair. Mn is the manifold and curly A sub max is the maximal atlas. We will always work with the maximal atlas. And one more thing, I will pretend that the maximal atlas is unique. Although in reality it is not so. Mathematicians will tell you that it is not necessary that the maximal atlas is unique. One can have multiple maximal atlases, and they give the same manifold different differential structures. So the point of differential, so in some sense, in the viewpoint of differential geometry, different maximal atlases for a given manifold should be thought of as different manifolds in general. As a topological space, they are same, but as manifolds, if they have different structures, it's best to think of them as different manifolds. So I'm going to pretend that there is a unique differential structure or a unique maximal atlas. Okay.